Hello everyone, welcome back to Tech World with Sahana. Today we are diving into Chapter 5 of Kubernetes Zero to Interview Hero series, Services and DNS. So here's a list of all the topics that we are going to cover today, plus 10 scenario based questions on which service to use for what type of application flow. So let's get started. Let's start with our first topic, why services exist. In Kubernetes, pods are not permanent. They can die, restart, or even gets rescheduled on different nodes. Each pod gets its own IP address, but those IPs are temporary. Imagine you have a front-end application trying to talk to back-end pod. If the back-end pod restarts, its IP changes, and the front-end won't know where to connect. That's where a service comes in. A service provides a stable virtual IP, we also call it a cluster IP, while the service exists, no matter how many pods come and go. The service automatically keeps a track of the pods behind it using labels and selectors. So traffic always gets routed to the healthy pods. So in short, pods are dynamic, services are stable. Services are the way Kubernetes gives us reliable networking inside a cluster. Now let's talk about the default YAML for services. API version v1. This specifies the version of the Kubernetes API used to define service object. For services, Kubernetes requires using API version v1 because they belong to the core API group. Kind is service. This indicates that we are creating a service resource which exposes a set of pods as a network service. This name is the unique name of the service used for DNS resolution and resource identification within the cluster. Selector defines the label selectors to target specific pods. The service forwards traffic to pods that matches these labels. Port is the port number exposed by the service inside the cluster. Clients use this stable port to access the service. Target port. This is the port on the selected pods where the application is actually listening. This allows the service port and the pod port to differ if needed. Protocol, we are using TCP. This specifies that the network protocol used for communication is TCP. Well, the default is also TCP, but UDP can also be used if required. So at this stage, with this YAML, this service will create a cluster IP by default, which is only accessible inside the cluster. Next topic is cluster IP. So what is a cluster IP? By default, when you create a service without specifying the type, Kubernetes makes it a cluster IP service. This gives the service a virtual IP address that is accessible only inside the cluster. That means other pods and services inside the clusters can reach it. But you cannot directly access it from your local machine or from outside the cluster. We use this when we want an internal communication. For example, a front end talking to a back end or a back end talking to a database. Think of cluster IP as intra-cluster communication only. So now let's again look at this default service YAML. We have just added this one line. Type is cluster IP. This explicitly sets the service type as cluster IP. Even though when you don't mention, this will still take as cluster IP because it is default. And nothing else changes. Kubernetes will automatically assign a stable cluster IP address to this service. So let's have a quick recap. Cluster IP is the default service type used for internal only communication. This provides a stable IP and DNS name inside the cluster. Next we have is NodePort. A NodePort service exposes your application outside the cluster. It does this by opening a port from a range of 30,000 to 32,767 on every node's IP. When you hit any node's IP at that port, Kubernetes forwards the traffic to the service, which then routes it back to the backend pods. So now, instead of being cluster internal only, your application is reachable from outside, though it's still not the production grade external access. Think of NodePort as access your application from outside the cluster using node IP colon NodePort. Now let's check out the default YAML for NodePort. So if you see now, instead of type cluster IP, we have written type NodePort. This tells Kubernetes to expose this service on every node. And then we have added this line NodePort colon 30,007. Manually assigns a port, and if not given, Kubernetes will automatically pick one from the range we discussed earlier. Now you can access your application from this URL, node IP 30,007 from outside the cluster, and my service colon 80 from inside the cluster like cluster IP. So let's have a quick recap. Cluster IP is internal only. NodePort makes your application accessible from outside via node IP colon NodePort. Let me give you an example scenario. If you are running Kubernetes on Minikube and you want to test your application from your laptop browser, NodePort works perfectly. Next we have is Load Balancer service. A load balancer service exposes your application outside the cluster using a cloud provider's load balancer, like AWS ELB, Google Cloud's load balancer, Azure's LB. The cloud load balancer gets a public IP, and all traffic to that IP is routed into your cluster, then forwarded to your pods. You don't need to know nodes, IPs, or ports. You just get one clean external endpoint. Think of load balancer as production ready external access with a cloud load balancer in front. So now let's check out the default YAML for this load balancer. If you see, we have used this time type as load balancer. This tells Kubernetes to provision a cloud load balancer. The service then automatically creates a cluster IP and a node port behind the scenes. The load balancer then forwards traffic to that node port, and Kubernetes routes it to the pods. And then you get a public IP and DNS name from your cloud provider. So that's how load balancer works in cloud environment. So now let's see how we can achieve this in on-premise. So if you are running Kubernetes in your own data center or on local tools like Minikube, there's no built-in cloud load balancer. That means a service of a type load balancer won't work out of the box. So what you need to do instead is either use NodePort plus external load balancer. You can expose your application with a NodePort and then use your own load balancer like HA proxy, Nginx, or F5 to point traffic to those node ports. Or use MetalLB. This is a Kubernetes add-on that gives you a cloud-like load balancer behavior. It works by assigning an external IP from a pool that you configure, so your on-premise cluster can act just like a cloud one. So in short, in cloud, load balancer works automatically. For on-premise, you either combine NodePort with your own load balancer or install MetalLB for a native solution. So let's have a quick recap. Cluster IP for internal access only, NodePort is for external access, load balancer is for external access via a clean public IP. On-premise it needs a turnaround with MetalLB or external LB. Now let's start with what is a headless service. Normally Kubernetes service gives you a stable virtual IP or a cluster IP that load balances traffic across pods. But sometimes you don't want load balancing or a virtual IP. Instead, you need to connect directly to pods themselves. That's where a headless service comes in. With headless service, no cluster IP is assigned. Instead, returns the individual pod IPs. Think of this like a skip the middleman, connect straight to pods. Now let's check out this headless service YAML. Cluster IP is set to none. This is the key difference. It tells Kubernetes not to assign a cluster IP. Instead of one virtual IP, the service creates DNS records for each pod. For example, if you query this, DNS might return multiple pod IPs such as these. So let's check out where are these helpful. So you can use a headless service for database connections like systems like Cassandra, MongoDB, or Kafka need clients to talk to specific pods, not through load balancing. Or for a stateful set, where each pod has a unique identity, like these two. And headless service allows client to resolve and connect to those specific pods. So let's have a quick recap. A headless service has no cluster IP. DNS gives you the pod IPs directly. Use it when application need direct pod level access instead of load balancing. Now let's check out what are service selectors. A service doesn't connect to pods by their names or IP address. Instead, it relies on labels to decide which pod belongs to it. This is controlled by the selector field in the specification. The service matches pod with the same labels and automatically routes traffic to them. Think of this like selectors are matchmaking systems between services and pods. So let's check out these YAMLs and see how the connection works. The service looks at its selector. App, my app. It finds all pods with the same label. Kubernetes automatically creates endpoint pointing to those pods IPs. Any request sent to the service is forwarded to one of those pods. Now, what if there's no selector? Well, you can also create a service without a selector. In this case, Kubernetes won't auto-discover pods. You must manually define an endpoint object to tell the service where to send the traffic. This is especially useful when pointing to an external service outside the cluster. Let's have a quick recap. Service selectors decide which pods the service routes traffic to. Pods must have matching labels for the service to find them. If there's no selector, then you need to manually link pods or external systems via endpoints. That brings us to our endpoint object. So, what are endpoints? So, when a service finds pods via selectors, Kubernetes automatically creates an endpoint object. This object keeps track of all the real pod IPs and ports that the service points to. Now we will check two sections here, auto-created endpoint and manual created endpoint. First, let's see how do auto-created endpoint work. We first create a deployment with 3 replicas, so we actually have 3 pods in the cluster. This gives us 3 pods all with the label app my app. For example, they might get IPs like these. We now create a service with a matching selector. Notice that how the service has a selector app my app. This matches the pods created by the deployment. Kubernetes then automatically creates an endpoint object for this service. You don't write this yourself. Kubernetes fills it in automatically because the service had a selector. The deployment created pods with the matching label. So to summarize clearly, pods come from deployment YAML, service YAML has a selector that matches those pods, Endpoint object is automatically created by Kubernetes listing the pod's IPs. So now let's understand if we have no selector in service. We create a service without a selector. Notice that there's no selector field here. Because of that, Kubernetes has no way to know which pod this service should send traffic to. So Kubernetes will not create the endpoint automatically. We manually create the endpoint object. Here, the metadata.name must match the service name, that is the external DB service. We explicitly list the address, this, and the port, this, of the external resource. This tells Kubernetes whenever something connects to external DB service, forwards the traffic to this. Let's understand how it works inside the cluster. Pods can now connect to the external DB service. Even though there are no matching pods in the cluster, traffic will go to the external database. So let's quickly summarize this. With selector, endpoints automatic created. Without selector, you must manually create an endpoint. Useful when pointing a service at external systems like databases, APIs, or services not managed by Kubernetes. Now let's understand what is CoreDNS. CoreDNS is the DNS server inside the Kubernetes. It runs as a deployment in the cluster, that is in the kube system namespace. Its main job is to resolve service names and pod names into IP addresses. Well, thanks to CoreDNS, you don't need to remember the cluster IPs. You can just use names like this. My service default SVC cluster local. Think of CoreDNS as the phone book of Kubernetes networking. So let's understand how this works. First, a pod makes a DNS request for my service. Then CoreDNS checks the Kubernetes API and finds the service. Then it replies with the cluster IP if it's a normal service and the pod IPs if it's a headless service. Let's understand this service DNS naming convention. So this is the full DNS name of the service. Here my service is the service name. Default is the namespace, and this complete is called DNS name. But usually pod in the same namespace can just use like my service and it would work. Next we have is pod DNS. This is less common, so let's just understand it quickly. Pods can also have DNS entries if enabled. This would be the format, and this is mostly used in stateful set and headless services where pod identity matters. Next is CoreDNS config map. CoreDNS behavior is controlled via the CoreDNS config map. You can also customize it to forward DNS queries outside the cluster, configure split DNS, add custom internal DNS zones. So let's have a quick recap. CoreDNS is the DNS server for Kubernetes, resolves services and pods into IPs. The naming pattern is this and makes service discovery seamless. Moving on with our last topic, service discovery. Service discovery means how do pods find and connect to each other without knowing IPs in advance. In Kubernetes, this is automatic thanks to services plus CoreDNS. Pods don't care about pods' IPs which change. They just use service names. So service discovery is basically using stable service name instead of dynamic pod IPs. How service discovery works in Kubernetes. Let's say we have a front-end pod that need to talk to a back-end pod. Instead of remembering pod IPs, the front-end just sends a request to back-end service port 80. Now behind the scenes, CoreDNS steps in, resolves the name backend service to the service cluster IP. The service then looks at its endpoints list and forwards the request to one of the backend pod. And the best part, even if those backend pod restarts, change IPs, or move to a different nodes, the service and endpoints mapping takes care of it automatically. So as a DevOps engineer, you don't worry about the pod IPs. You just use the service name and Kubernetes makes sure the traffic always reach the right pod. And Kubernetes actually gives us two different ways to discover services inside the cluster. The first way is environment variables. Whenever a pod starts, Kubernetes automatically injects environment variable for any existing service. For example, you might see something like these. But there's a catch. This only works for services that were already created before the pod started. That brings us to our second way. The one most people use is DNS. Here's where CoreDNS comes in. It resolves service names into IPs, so you can simply connect to something like my service instead of memorizing cluster IPs. This method works for all services, is dynamic, and much more reliable. That's why in almost every real-world application, DNS-based service discovery is the standard. Now let's see an example. Let's say you have deployed a service called DB service in the default namespace. Now, any pod inside that namespace can simply connect to it using the short name DB service. And if you are in different namespace, you can still reach it by using the fully qualified DNS name, something like this. That's how Kubernetes makes service discovery seamless. Short names when you are local, full names when you need to cross the namespace. Now the top 10 scenarios you have been waiting for. Which service to use for what type of application flow? Scenario 1. Imagine you have a React frontend pod that needs to connect to a Node.js backend pod, and both are inside the cluster. The right choice here is ClusterIP. Why? Because it gives you stable internal communication and you don't need to expose anything outside the cluster. Scenario 2. Suppose you are running Minikube on your laptop and want to check the application from your browser. The right choice here is NodePort. Why? Because it's the simplest way to expose your application to your local machine, making it easy to test from outside the cluster. Scenario number 3. Let's say you are deploying a public-facing API in a cloud environment. The right choice here is LoadBalancer. Why? Because the cloud provider automatically provisions a managed load balancer with a public IP or DNS, making it production ready. Scenario number 4. Suppose your cluster is running in your own data center with no cloud provider. The right choice here is NodePort with an external load balancer or using Metal LB. Why? Because there's no built-in cloud load balancer, so you need a workaround to distribute the traffic reliably. Scenario number 5. Imagine you are running a database where each pod has its own unique identity. The right choice here is a Headless Service. Why? Because it gives you direct DNS record for each pod, allowing client to connect to individual database nodes. Scenario number 6. Suppose your application inside Kubernetes needs to connect to a PostgreSQL database running outside the cluster. The right choice here is a service without a selector, plus a manual endpoint object. Why? Because the service name acts as a stable DNS inside the cluster while still pointing to the external database IP. Scenario number 7. Imagine you are rolling out version 2 of your application while version 1 is still live. The right choice here is ClusterIP with different selectors. Why? Because selectors let you target specific pods, so you can split traffic between versions safely. Scenario number 8. Internal microservice architecture. Suppose you are building a microservice application with dozens of internal components talking to each other. The right choice here is ClusterIP. Why? Because it keeps all services stable and accessible internally without exposing them to the outside world. Scenario number 9. Sometimes you want to connect to a specific pod, for example, when debugging a stateful set. The right choice here is a headless service. Why? Because it gives you the actual pod IPs through DNS instead of load balancing traffic. Scenario number 10. Imagine you have a database cluster that should be used by internal microservices, but admins also need external access. The right choice here is a combination of ClusterIP for internal clients and Ingress or Load Balancer for external users. Why? Because this setup separates internal and external traffic, keeping it both secure and flexible. So, the final wrap up. ClusterIP is for stable internal access. NodePort is for basic external access. Load Balancer is for cloud-based production workloads. Headless Service are for direct pod level access. Endpoints let you connect to systems outside Kubernetes. So that is it for today's chapter. Hope this was helpful. Drop comments, any questions you have, and see you in the next one.